ME412 The Amazing Heat Pipe by Emma Drenth, Ben Lindemulder, and Jamie Steinberger. Heat pipes are a simple and reliable way to provide cooling. The function of a heat pipe is based on the evaporation and condensation of a working fluid housed within the device. A typical horizontal heat pipe is pictured here. A heat pipe operates by boiling a reservoir of working fluid housed within the pipe at one end, and then it allows the working fluid to condense at the opposite end of the pipe. This condensation of the working fluid releases latent heat, which acts to remove energy from the hot reservoir. Copper was selected for our heat pipe because of its high thermal conductivity, availability, and reasonable price. Distilled water was selected to be the working fluid of our pipe because the operating range of the water encompasses the operating range stipulated within the project requirements. 2 ball valves were included in the construction of this heat pipe. One ball valve acts to isolate the working fluid reservoir at the bottom of the pipe. When this valve is closed, it is possible to remove the air in the condenser chamber with a vacuum in order to create a low pressure environment. Once the vacuum has created a low pressure in the condenser chamber, the second ball valve can be closed. Once the first valve is opened again, the working fluid will be exposed to a low pressure environment, which is critical to the operation of the heat pipe. This low pressure environment will lower the boiling temperature of the working fluid within the pipe, making the heat pipe effective for a more applicable range of temperatures. In order to calculate the theoretical values for our heat pipe, we used the top equation seen here to calculate the maximum heat transfer rate of the heat pipe, and the bottom equation seen here to calculate the effective length. The theoretical values for our heat pipe can be seen here. It can be seen that the maximum heat transfer of our heat pipe was calculated to be 112.28 watts. Our experimental heat transfer rate was calculated using the top equation seen here. Comparing this heat transfer rate to the theoretical value we calculated earlier, we found an error of 27.4% when our design included the PVC sleeve. Since our error was higher than we expected, we decided to remove the PVC sleeve to expose more of the copper to the ambient air. After doing this, we found an experimental error of only 13.3%. We recorded the temperature of the water with the heat pipe in it after every minute during our experiment and compared it to natural convection. It can be seen here how effective the heat pipe is in accelerating the cooling of the water. Heat pipes are a reasonable option to accelerate cooling when compared to natural convection. Heat pipes can be used for many applications since the working fluid and dimensions are extremely flexible. When compared to heat exchangers, heat pipes are also easier to construct and maintain. Here's our references.